So let's continue that example with that fair coin, or rather unfair coin, as we're going to prove it. We went through pretty much all of the steps, but some little things were missing. So what we're going to do in this video is kind of go back through that example more officially. And these will be the steps that we're expected to follow as we go through hypothesis test for a single proportion. So we just want to fill in some blanks here. So with an actual hypothesis test, our first piece is going to be to set up the null and alternative hypotheses, which we did in that last video. But just to show how we'll officially write it out, for this first step, I would go null hypothesis, h with a little subscript of 0. And then our null hypothesis is that p is 0.5. So p equals 0.5 to represent that we assume the proportion of heads is 50%. The alternative hypothesis, which we want to prove, this is what we want to find evidence for. This is going to be that p is more than 0.5. So this is to represent an unfair coin where the proportion of heads is more than 50%. And that's it for step 1. So that's the notation we'll fill in for setting up the null and alternative hypotheses. Next piece is checking the central limit theorem. So this is one thing I didn't do in that last video that I really should have before I started using a bell-shaped curve. Part of this is that we have to prove that we pass the conditions in order to have normally distributed data. So we need to check independence. We need to check randomization. We need to check that we have a large enough sample size, or we could think of this as our success failure. Okay, so this should be looking similar to our work with confidence intervals. And just like with confidence intervals, with independence and randomization, let's go ahead and just check those off. We're good. I'll give you examples that only have those met. So we'll assume we're all good there. Success failure, what we need to do is take our sample size times P and Q. Now what's tricky here is because in the background, when we're originally given this problem, we have a sample size of 50 and we have a P hat of 0.75. So we kind of have two values for P floating around here. We have P hat and we have this assumed value for P of 0.5. And something I said in that last video a few times, but I just want to call it out more distinctly here. When we make that bell-shaped curve, it's all built around that null hypothesis. We built it around that 50% coming through because that's what we're assuming is true. And we want a distribution built around that assumption so we can see what do we expect for our sample proportions. So checking success failure, we do not want to use our sample statistic. Instead, we want to build everything around this null hypothesis. So I'm going to use 0.5 for P and 1 minus 0.5 for Q, which is just also 0.5. I really only need to do that once, but hey, here we are. Okay, more than or equal to 10, more than or equal to 10, and we're good there. So all that tells me is that I can go use a bell-shaped curve. Yay. Okay, two little pieces here. We're going to build the sampling distribution, which is something we did in that last video. The new thing is calculating a test statistic, and I'm going to go ahead and save that for the end of this video. What we'll get at is there's two different ways to go about these. Whichever way you want to go about it, you should get the same answers at the end. But I'm going to go with this sampling distribution method just to link up with what we did in that previous video, and I'll come back to the test statistic after we finish up this video. Okay, so building the sampling distribution, that means I need my mean and I need my standard deviation. So mean is equal to our population proportion. Again, we're just working with our assumption here. So I keep referring back to that null hypothesis for absolutely everything. I basically ignore that sample statistic for as long as I possibly can. I'll show you the exact moment that comes in, but until then, we ignore that 0.75. Everything is about that 0.5 right there. So, P of 0.5, 0.5 times 0.5 over sample size of 50, which is a 0.0707. Oh, and just as a reminder, so mean is equal to our population proportion. I'm going to put a little 0 right there to show that it's coming from the null hypothesis. Standard deviation is the square root of P with that little 0 times Q with that little 0 over our sample size of N. Okay. So this builds my sampling distribution. I have mean, standard deviation. I even have a nice picture to work with here. And in fact, for calculating the p-value, I can go back to my picture that I used here, specifically the one I used on this left-hand side in that left video. Calculating the p-value, so p-value is area under the curve. That's what's important to remember. So when it says calculate p-value, the equivalent is calculate the area under the curve. And what we want is our sampling distribution that we just built. And then this is where the 0.75 finally comes in. We want to set that 0.75 as a cutoff. So to calculate the p-value, what we're going to do is we're going to need to go to Staplet here. So we need to go to Staplet with our sampling distribution. So we're setting it up with mean of 0.5, standard deviation. So let's go ahead and do that, which I actually already have plugged in here. So normal distributions. For p-value, we want to calculate an area under the normal curve. Let's go ahead and make a note of that. And that area, we want to find the probability of being at 0.75 or more extreme than 0.75. And that's going to create a right tail area for this picture. So again, 0.75 is off the screen there, but let's see what we get out. So my value for the cutoff is 0.75. I'm going to calculate that area. I'm going to go ahead and show some information here so I can see the teeny tiny area of 0.02%. And I'm going to go ahead and grab a screenshot of this so I can draw it a little bit and we can see all those pieces coming through here. So here's all my information right here in a nice picture. Okay, so let's go ahead and put that over here. So from this information that we're getting from Staplet, we have our sampling distribution plugged in. This is where p hat goes. So we save p hat until we get to that point and we plug it in as our cutoff value. And then what we're interested in is this area right here. That area is our p-value. Now I know we get to a point in this where there's so many different p's floating around. We have our population proportion, we have our sample proportion, and now we have a whole new thing called p-value. And it's just unfortunate, but that's the way it goes. So calculate the p-value. We end up with p-value equals, and we might sometimes need the decimal form, so I'm going to go ahead and write that out, of a 0.0002. Or you could think of this as 0.02%. So what does this p-value mean? If we think about the distribution we have, this is coming through as a probability, so this is a % chance because it's area under the curve. So how I would translate p-value in this case is if I had to make a sentence for it, I would say if the coin is fair, so under that null hypothesis, if the coin is fair, if our assumption is true, there is a 0.02% chance of seeing our sample results, or more extreme. But in short, it's just saying if our assumption is true, if that null hypothesis is correct, we witnessed something that had a 0.02% chance of occurring. Almost 0% chance of occurring. So what we're seeing here is a very small p-value, which means if there's such a low probability, I don't think this coin is fair. That's statistically significant. So this is where we reject the null, and we have found statistically significant evidence for the alternative. So all of those come through with that p-value coming through. So when we have that p-value, it's going to be shorter work than what I'm writing out here. I'm just trying to give information where I can. But that p-value, we take a look at it. We figure out if it's large or small. I'll talk about that cutoff for when it's considered big versus small. But if it's small, we reject the null. We have evidence for the alternative. And I just make notes of those things to help me when I go to this last step, which is to write the conclusion. All right, the conclusion. I usually start off with a piece of reject the null or fail to reject the null. In this case, we are rejecting the null hypothesis. So I'm just going to say reject the null hypothesis. Then what I want to do is make a sentence where I include the p-value because that's our evidence. So like I said, if the coin is fair, there's a 0.02% chance of seeing our sample result or more extreme. It's not impossible for that to happen if the coin is fair. It's just so incredibly unlikely that we're thinking that's not the case here, that we have an unfair coin. But there's always a chance that we're incorrect, and the p-value is the number that tells us the kind of the likelihood of us being incorrect. So we want to always include, just like how with confidence intervals we said, we're 95% confident, 99% confident. Same thing here, we're kind of using this number to say, okay, we're making this claim, but here's the kind of possibility that we're incorrect here, that an error is occurring. So I always start with a p-value of, and then we state our p-value. I'm going to go with 0.0002. So then I can see that number and be like, whoa, that is a very small, that's very close to zero. Like, this is pretty significant. And then I would say, I want to make a sentence about what's happening with the alternative hypothesis. So it's either we have evidence for the alternative or we do not have evidence for the alternative. So what I would say is there is evidence. And I don't want to just say there's evidence for the alternative hypothesis, because anyone reading that sentence would then go, what's the alternative hypothesis? So what we want to do is take that alternative and put it back into context. In this case, when I'm looking at this p more than 0.5, what that's representing in context is an unfair coin. And that's how you want to phrase it, so that people could read that sentence and understand what we proved here. Okay, so there is evidence the coin is unfair. We could leave it at that. We also technically proved that it's showing a proportion of heads significantly larger than 0.5. We could throw that in there, but we can leave it just like this. There is evidence the coin is unfair, and put just like that. And then seeing that 0.0002, we can see that's pretty significant evidence. In fact, we could even throw in wording here if we wanted to of there is strong evidence. But once we kind of talk about a scale for where we reject that null hypothesis, we can talk about adding those words in there. Okay, and you might be like ready to pause the video and done, but I have to go back to the test statistic, which is something I'll talk about in future videos, but it is part of our quest for answering this. It isn't necessary, but there's going to be times where you're asked for the test statistic, and I want to set you up for filling that in. So, a test statistic. This is a z-score. And if you remember, z-scores were calculated previously with x minus the mean over standard deviation, which is almost entirely still true, but a few things change. Actually, one thing changes. X is now a sample proportion. So how we would calculate our test statistic for this scenario is we would take our sample proportion, subtract the mean of our distribution, which is our assumption from the null hypothesis, and then divide by the standard deviation of our distribution, which would be that square root of 0.5 times 0.5 over sample size of 50. You want to keep this as accurate as you can for as long as possible here. But if we throw that in a calculator, let's see, separate my fraction. I'm just doing this off to the side here in my calculator. But we are going to get a value of 3.5355. And depending on the rounding that we're seeing, that number should be, it's a little off. And it's because we rounded the standard deviation as we plugged it in, but they're seeing that z-score. And what this means is you can go through this whole process that if you have that test statistic, you could then make a standard normal distribution with mean of 0, standard deviation 1. And then what you would do is you would use that as the cutoff for finding area to the right. You're going to end up with pretty much the same p-value. Both are fine methods. I tend to show examples using the sampling distribution method because I like that it keeps the number line in context of I can see this as proportion of coin flips, whereas when we go to 0, 1, we kind of lose that context. So I tend to go the sampling distribution route, but you're welcome to use the z-score. With that, just be careful of rounding, and if you go the sampling distribution route, you'll still need to know how to find test statistics, as it will be part of the process. But that right there is a full hypothesis test from flipping a coin 50 times and seeing a proportion of 0.75, and that leading to a proof that we do have an unfair coin, and it was pretty statistically significant. In the next videos, I'm going to break down these steps even more, give you some guidelines, and then we'll look at lots of examples.